Okay, everyone. Thanks for sticking around. I'm feeling a little bit drowsy, so I'm going to do a quick exercise here, and I'll invite you all to do it with me. So, this is a picture of the Sprague, I think, a similar time of year to now. So let's just imagine we're standing on the riverbank and we jump into that cold water. And we get all that oxygen flowing. Okay, great. So, I'm going to talk about temperatures in the tributaries of Upper Klamath Lake. This is the project that I did with my colleagues Jacob Kahn, who's here today, and Kate Perkins, who I think is probably on virtually, and was funded by the Klamath Tribes. I'm presenting today these distilled little snippets from this very long and detailed report. So if there's anything you want to know more about, or you want to know the whole story, read the report, but you're going to get part of the story today. I'm going to skip that. So the main data set that we're using here is the Klamath Tribes water temperature data set that they collected in the tributaries of the lake. We're supplementing that with additional data from the BLM and the Forest Service, DEQ, and then flow data from flow and temperature from USGS and flow from Oregon Water Resources and the flow from Klamath Tribes. But the Klamath Tribes temperature data set is the main thing that we're analyzing here. So here's a map of the 50-something stations. The program started around 2003. Some of these stations were only monitored for a year or two, and others have been continuously monitored throughout the whole thing. Here's just an example of the period of record for stations in one example subbasin, the Sprague. So you can see the Klamath Tribes data starts in the pale blue there in around 2003. So our first research question is, where and when does flow affect water temperatures? So to do that, we took all of the flow gauges that we had and we plotted them by day of the year. So here's an example for Sprague at Chiloquin. And for every day of the year, we split the flows up into, for that day of the year, what's a high flow, what's a medium flow, and what's a low flow. Then we go through and we mark all of our days according to this, and then we can plot the water temperature data according to what flow condition that it is. So here's an example for 3 sites. I'll start with the one on the left, which is the South Fork Sprague River at a picnic area, which is near the upper extent of the valley, right downstream of the canyon of the Sprague River Valley. And you'll see at this site, the red line is temperatures during a low flow condition. The blue line is temperatures during the high flow condition. And then the dashed black is the difference between those two. So in late May, early June at this site, it's 6 degrees Celsius warmer under the low flow condition than it is under the high flow condition. And so that site represents one kind of extreme end of the thermal sensitivity in terms of the effect of flow. There's a really big effect of flow there. And you'll notice, that late May, early June is the peak, and then there's kind of a bell curve going out to the side there of less effective flow as you get further and further away from that. The opposite extreme of the bookend is Spring Creek, which is a very large, gigantic spring that feeds the Williamson River, and it's cold all the time and it's high flow all the time, and so there's no flow-driven temperature variability because it's always the same. So almost every site in the study area falls somewhere between these two extremes of the open solar exposed river that gets pretty warm when flows are low, and Spring Creek, which is incredibly stable. There's a few sites that do different things, like the Williamson River below the Sprague. There you see the blue line in July and August. It's actually warmer under a high flow condition. And that's because when you have high flows at this site, it means you've got more warm water coming down the Sprague River, and it's diluting that cold water coming from Spring Creek down the Williamson River. So that's just kind of a weird site, but most things fall in between those two extremes. So now I'm going to take this the dashed black line from this picture, from these graphs here, and show you what that curve looks like for all 50-something sites in the study area. And they're divided up by subbasin, where every line is a different site. So you can see that flow has a much stronger effect on temperatures in the Spencer Creek and Sprague River. I think I forgot to mention the study area when I was showing that map. It's the tributaries of Upper Klamath Lake, as well as Spencer Creek, which is the tributary to the Klamath downstream of J.C. Boyle. So that's where flow has the biggest effect, is those two subbasins. Much less of an effect in the Wood and the Williamson and the west side, because those are colder, higher volume spring-fed areas. And the temporal timing of the flow effect, you can see if you look at the Sprague River panels there, that it peaks in that May-June time period. There's kind of a weird second peak that we just noticed yesterday when we were putting these slides together in September, and I'm not really sure what's going on there. I need to look into that more. Okay, so the effect of water rights regulation on the hydrologic effects of that. So we divided the study period up into two major eras. There was a pre-regulation era that ends in 2012, because in 2013, the Klamath Tribes won recognition for their senior water rights, and they were able to start enforcing those water rights and curtailing irrigation to protect in-stream flows. So that we're calling the start of the regulation era. There was a transition period due to the a pending water deal where the tribes agreed not to enforce the full water right for several years, from 2013 to 2016. That deal then, as everyone knows, fell apart. And so the Klamath Tribes, they started enforcing their full water rights in 2017, and they have been since then. From a science perspective, this is kind of tricky, because a clean experiment is like a clean break, right? There's a before, there's a major intervention, there's an after. That's kind of the opposite of what we have here. We've got water rights changing over time. Farmers started switching to groundwater when they couldn't use surface water. There was intensifying drought over the time period. So it's really a pretty difficult challenge to untangle all these threads. There have been some previous efforts to look at the hydrologic effects of this water rights enforcement. There were two USGS studies, Hess and Stonewall and Wood. They found, looking at the stream flow gauge data, that the water rights enforcement appeared to increase Sprague River flows a little more than 50 CFS. Then there was a remote sensing study by Bill Purdy that looked at the consumptive use in agricultural fields everywhere upstream of the lake, so not just Sprague, but also Williamson and Wood. And so if you take the seasonal volumes of the reduction in agricultural consumptive use and you kind of divide it over the time period and convert it to instantaneous rate, you come up with about 70 to 160 cubic feet per second. And then recently, my co-author Jake and Jeff Walker did an analysis of stream flow gauges around the Sprague River Basin and found that the regulation appears to increase flows by up to 50 CFS. That's in August, is the peak effect. It almost all appears to be coming from one place, and that is the North Fork Sprague Basin. There's one very large canal, and there's a gauge on it that didn't go in until the water rights stuff was already underway in 2015. So we don't know how much was going before, but the peak capacity of that ditch is about 50 CFS, which matches pretty closely with these numbers. But it appears that that's the biggest hydrologic change that's happened in the Sprague, is the substantial curtailments of this canal. For our analysis, we looked a lot at the stream flow gauge data. This plot here shows an example for Sprague at Chiloquin, where the dashed black line is the Klamath Tribes in-stream water right. Then there is the gray lines are the pre-regulation era, and the different colored lines are some years in the regulated era. So what we see is you can see those gray lines poking up above in the springtime, in May and June, during the pre-regulation era. And so what that means is that in the regulated era, we had generally lower snowmelt during that time of year, lower flows during that time of year. It was a generally drier climate. So we would have expected that with those lower springtime flows, that in the regulated era, we should also have lower flows in the late summer. But we actually see the opposite. We've got higher flows in August and September in the regulated era, which is suggesting that that's due to that water rights regulation. To confirm that, we looked at the Chihuahuan River, which is over the ridge to the east of the Sprague River. So it experiences a very similar climate. It's just the other side of the mountain. And there we see the same pattern of generally lower flows in the springtime, but there's not the same lower flow, or not the same pattern in the fall. We don't see those elevated August and September base flows. So that's another indication that these increases in Sprague River flow is regulation driven. We also looked at relationships between snowpack and river flow. So here's an example. We looked at lots of months, but I'm just going to talk about August today. So on the top panel, there's the black lines or black dots, and the black trend line is the pre-regulation era going back to the 1980s for Sprague River, where snowpack is on the x-axis, and then August flows on the y-axis. And you can see that, as you would expect, if there's greater snowpack, there's higher August flow. Then we get into the regulated era, and the curve has like flattened out, right? And even if we get a really low snowpack year, we're still having relatively high August flows in the Sprague. That's another indication of that regulation effect. See a similar thing at the Williamson River below the Sprague, and that's probably driven mostly by the Sprague being a large tributary of the Williamson. We also see a big increase in flow at the Wood River, and it's even greater than increase in the Sprague. It's about maybe over or about 100 CFS in those low snow years. I'm not going to show a graph here, but a lot of the diversions from the Wood sort of drain off the agricultural fields and go into 7 Mile Canal and drain back into Agency Lake. And we do see that in the regulated era, there's been a decrease in the flows of that Agency Canal because there's less water sort of cycling from the Wood. Okay, so now moving on to water temperature and the effects of that water rights regulation. So we categorized every water temperature site according to how strongly we thought its hydrology was affected by the regulation and the water rights. So we've got some sites that are upstream of all the diversions. There's some sites that are just like Spencer Creek is not included in the geography of the adjudication, so it wasn't affected. Then we've got other sites where, yes, there are some diversions, but if the diversions are a very low percent of the flow, it's not going to have a major effect. So those are sort of like three kind of indices or references that we can use to compare to the other sites that were affected by the water rights. So our first method is to compare 3 sites that had hydrology that we think was affected by the regulation, and then plot that against 4 sites that are hydrologic or our temperature indices that we think were not affected by regulation. So here's an example here of the North Fork of the Sprague at a site called 3411 Road, which is it's right upstream of that big diversion that I showed. And so it's water there is nice and cool, but then on the y-axis there, and that's a site that does not have many diversions upstream of it, but there is that big diversion downstream. And so this next site is several miles downstream, and it's warmed up pretty significantly. And then during the regulated era, its temperature has decreased about 2 degrees C relative to that upstream station. So as that big diversion has been curtailed, there's a bigger volume of water flowing downstream, and so the water doesn't warm up as much by the time it reaches that next downstream station. But this is really the only site where we saw a big dramatic effect. In fact, we didn't really see much of an effect at all at the other sites that we had data to look at. As we don't have continuous data on all of those sites. We're really just looking at a sample of sites. So there could have been other sites that had big effects that we just didn't have data for. But of the sites we had data for, this was the only one that showed that big effect. So we also used statistical models, places where we had local flow, and we had a local flow gauge, and the Klamath Tribes had an in-stream claim. We developed a statistical model to predict temperatures as a function of day of the year and air temperature and flow and the site. And then we modeled temperatures under 2 scenarios. One is the gauged flows that were recorded, and another that was, well, what if we could meet the in-stream claim, then what would temperatures be if that claim could be met? So here's our friend again, the Sprague River at Chiloquin. That dashed black line is the in-stream claim. So one scenario uses these flows as an input, and then the other uses, okay, like any flow that's below the dashed black, if we bring it up to the black line so that everything is at the black line or above, what would the temperatures be? And then what's the difference in predicted temperatures? So we predict that the Sprague this site would cool by a little over up to 2 degrees Celsius if the in-stream claims could be met. We also use remote sensing. When Bill Tinnis was reviewing our draft report, he said, well, yeah, it does seem to be true that the temperatures in the Wood River, didn't get colder when the flow went up by 100 CFS because they're always cold. But he said, I think that those higher flows have increased the volume of the thermal refugia in Agency Lake at the mouth of the Wood. And I've been working a lot with remote sensing data. I thought, oh, there's some data out there that we can actually test this with remote sensing. And so we were able to show that actually during that full regulation period, that the size of the thermal refugia at the mouth of the Wood River has increased and it's cooled down. And that could be really important for the red band trout population as well as potential future salmon reintroduction. Even though it did not cool down the river, the water within the Wood River, it expanded the thermal refugia. We also looked at the suitability of temperatures for native salmonid fish. I'm just going to show one example here for juvenile Chinook, but we looked at other species and other life stages in the report. So here's a categorization of this is split by subbasin with every site being a different line there. So you can see in the Wood and West Side subbasins, it's some really cold water, almost all within the optimal range for juvenile Chinook rearing. And then in the Sprague River, during the middle of the summer, it gets pretty hot, and most places have temperatures that are stressful or severely stressful. This is just the sites that we have data for. Obviously, there's all those springs that provide cold water refugia at different places along the Sprague. So I don't mean to suggest that Chinook salmon will not do well in the Sprague River, but just at those main sites that we have, the temperatures get pretty warm. Spencer Creek has intermediate temperatures, and then the Williamson River has a really nice range of temperatures from really cold to really warm or medium warm. So in conclusion, the effect of flow on water temperature varies by site. In Sprague and Spencer, it has a really strong effect, less effect in those cool spring-dominated areas. We did see about 2 degrees Celsius cooling at that one site on the North Fork due to apparently to the shutdown of that large diversion. But we didn't see a lot of major changes elsewhere in temperature. Even though the surface irrigation has been substantially curtailed, groundwater use has expanded, and a lot of the sites their flows are still not meeting the in-stream claims. But we think the models show that if those flows could be met, that there could be further decreases in temperature in the Sprague River of up to 2 to 3 degrees Celsius. I'll just end here. If you're interested in this stuff, we got a lot of reading for you to do. And I want to also thank some acknowledgements. Bradley Parrish at the Klamath Tribes. He managed the collection of a lot of this data and helped us understand questions about the sites and about the water rights, and it was really helpful. Mark Buechner, helped get the project rolling. Megan reviewed our draft report and gave some excellent comments on that. And then Bill Tinnis would review the report also. So thank you for your attention. I'll take any questions. Yes.
Williamson's broke into 2 sections, the upper section being a lot different than the lower. Curious why you're not looking at the upper Williamson.
I mean, we do have sites in the upper Williamson. Oh, sorry. Yeah, we did include sites in the upper Williamson. Yeah. We have from the head of the spring at the top of the Williamson all the way down. Yeah.
And as far or is it lack of representation in the analysis?
Oh, yes. I don't know if I have a good graph that shows that well. Basically, the Williamson River monitoring program did not really start until around 2012, 2013. So we might have one partial pre-year of data before the water rights enforcement. So that was a part of it, is that Sprague River was really the sub-basin. That was really the only place where we had ample pre-regulation data.
I'm here from Stillwater. So I'm curious, is there any reason to think that if you had a few more years of data, you might see an effect? It doesn't sound like you're saying I just have enough information. I don't know if there really was an effect. It seems like what you found in modeling is that there were only a few locations or one location where there was an obvious effect. So is it, or as climate change progresses, do you think that effect will be erased, or kind of what are your thoughts on it?
I mean, I think there probably are more sites out there where we didn't have the data where there would be an effect. Let's see what else to say about that. One thing I think we could have done more of is the analyzing. We pooled the regulation era for most of our analyses. If I had the time and energy to go back and do it over, I would have done more stuff where we did some pooling it all, and then also some of the partial regulation, some of the full regulation, because there could be some more things that become detectable, at least at full regulation, I think, with the data that we have.
Have you used are you using thermography to map the springs, cold springs, or the streams?
Yeah, there certainly has been, I think, 2 rounds of flights. One during the TMDL was in the 2001 or 2000 time period, something like that, an aerial infrared flight. And then there was another that the Klamath Tribes did in 2007, I think. So there is that data available. We just couldn't really use it in this type of time series statistical analysis for our report, but that information exists, yeah.
It would be interesting to see the era of increased groundwater pumping affect on the springs.
Right. Yeah, I don't think we have any since that increased groundwater era, so might be something to redo in the future. All right, well, thank you.